In the last class, we looked at various crystal structures, the 7 crystal systems, and the Travis lattice associated with all these crystal structures. And we looked at a basic scheme to remember the unit cell characteristic of each crystal system. So just to revise, cubic is suppose you have a cubic. So cubic means you have all the, in a 2 dimension. If I show, I don't know if I'm visible to you. Okay, so this is a cube in 2 dimensions, that means a square. So if I stretch it one side, it will become tetragonal, something like this. Okay, and if I stretch from the other side also, now because the one side y-axis and the z, they are equal. Okay, so if I suppose stretch from the other side also, so that all the sides become unequal, it become orthorhombic, right? So from cubic, tetragonal, tetragonal to orthorhombic, and triclinic, where A, B and C are unequal. So these two, triclinic and cubic, we need to remember. And from the cubic uh, we can extract, or we can reach to tetragonal by one transition, by changing one of the side to be unequal, and from tetragonal to orthorhombic, the other side also unequal, and all the angles remain the same. If we take the cube and twist it, stretch it along the diagonals, body diagonal, not the face and face diagonal, but the body diagonal of the cube, then what will happen? Sides will remain same, but angle will change. Okay, so that is known as, or either rhombohedral or trigonal. So that is the uh, A is equal to B is equal to C, and alpha is equal to beta is equal to gamma, but not equal to 90 degree. So by same amount, if you pull or push the body diagonal, then these angles will be equal, but they will be different than 90 degree. And from the triclinic, if we so, and in the triclinic, we have A not equal to B not equal to C. These are the, initially all the parameters are unequal. So this is triclinic. And from the triclinic, if there is one of the angle, I mean, what you have done is monoclinic. Mono means only one of the angle is non-equal, and other two are equal to 90 degree. Okay, so that way you can reach to monoclinic. Or from the orthorhombic also, because all the sides are unequal, all the angles are all the sides are unequal, and all the sides are all the angles are equal, all the sides are unequal. So from orthorhombic to monoclinic, if we change the one of the sides, one of the angle, so that the angles becomes unequal, so that's a monoclinic. And both the angles becomes unequal, then it's a triclinic. And then hexagonal. Hexagon, from the name we know what is a hexagon. So in each angle in the hexagon is 120, and other two are 90 degree. So this between A and B and B and C, the, alpha and beta is 90 degree, and gamma is 120 degree, and two sides are equal. So A is equal to B but not equal to C, that is the vertical side. So this way we can remember all the crystal systems. Now these are the 7 crystal systems. but there are total 14 Bravais lattices. That means the unique arrangement of the point in the 3 dimensions that are unique. Okay, so for example, triclinic only simple cubic. That means atom at the corners. That is the Bravais lattice. There is no other possible. So if you look at the Bravais lattices, so in case of cubic, we have primitive, that means the simple cubic. Then we have the body centered, and then we have the face centered. So I, uh, P, I and F. P for primitive, F for face centered, I for body centered cubic. So in case of cubic, we have simple cubic, body centered and face centered. These are the Bravais lattice associated with the cubic. And then with the tetragonal, because one of the side is now stretched, so all the face center atom at the face center not equivalent. So this face center, this geometry is not a Bravais lattice. So only simple tetragonal orthorhombic, but tetragonal simple cubic and body center is there, and in orthorhombic was the other side also stretched, and then this basically becomes the face center again becomes equivalent, and so we have the simple cubic, body center, face center, and the end center. So these are the end center of base center is also said. Sometimes to maximum Bravais lattices are possible in case of orthorhombic, and the hexagon only one primitive, and similarly trigonal, which is rhombohedral, only one, that is a primitive unit cell. Primitive unit cell is a Bravais lattice, and monoclinic there is a base centered, and the primitive simple cubic primitive, and in the triclinic only primitive unit cell is the vector. So in all 7 systems we have a primitive unit cell is by default is the Bravais lattice. In addition to that, there is a base center or body center or face center. So body center, face center and base center, these are the 3 additional configurations Bravais lattices that are possible in say cubic, tetragonal, orthorhombic and monoclinic. All other means hexagon, rhombohedral or trigonal and triclinic, they have only primitive Bravais lattice as the possible unique arrangement of the lattice point in the 3 dimensions. Okay, so these are the 14 lattices, and now how do we basically characterize or represent these lattices, these crystal structures in a mathematical form? Okay, so these forms are known as Miller indices. We have the a unique arrangement of the lattice point in 3 dimensions. Okay, so that means by repeating that arrangement in 3 dimension along x, y and z direction, we can recreate the whole 3-dimensional crystal structure. Okay, so now how do we mathematically look into it so that these numbers can be processed, the other information can be extracted? So this Miller indices, Miller gave these indices, so these are the Miller indices. So plane in lattices and Miller indices. So it's the essential concept to understand the diffraction of X-rays. Now there is a theoretical construct that the atoms are periodically arranged. There are experimental evidences including the X-ray diffraction. So we know what is diffraction. and now X-ray diffraction, because again the basic condition for diffraction is satisfied in case of X-ray diffraction. And what is the basic condition? That wavelength of the electromagnetic radiation, that means X-rays, is of the same order as compared to the interplanar spacing. So if this is a plane, this is another plane, so there are multiple planes that are possible. So let me, so these are, suppose, one set of planes that are possible. These are other set of planes that are possible. Then this is another set of planes possible. Okay. And in the same lattice, so A, B and C is the same lattice, but different possible planes are shown by joining the lattice points by these lines, which are either densely packed or in A, B or C. So there are three different arrangement in A. Similarly, we have another set of planes in, which is say number 4, and then we have number 5 as the different set of planes in C. So in each lattice, depending upon from where the observation is done, you will find the unique arrangement of the planes in the lattice. So how do we mathematically look at it? How do we experimentally verify whether there is a periodic arrangement or there is not a periodic arrangement? Okay, so to verify this, X-rays come very handy, because the wavelength for X-rays is of the order of the interplanar spacing. So for example, this is copper alpha radiation. The wavelength of copper alpha, the X radiation generated from the copper target is 1.54 angstroms, and this is of the same order as the interplanar spacing in the crystals. So when that means, if suppose this is the interplanar spacing D, so D interplanar spacing is of the same order as lambda. Okay, so once this condition is satisfied, then electromagnetic radiation can be used to find out various parameters. For example, the interplanar spacing, the concentration of such planes, and so on, to present in the crystal. So essential concept required to understand the X-ray diffraction by crystal lattices is the Miller indices in the presence of planes and family of planes. Each plane is constructed by connecting at least 3 different points together. Because of the periodicity of lattice, there will be family series. ये family के बारे में हम बात करेंगे. Family means, suppose there are one type, number 1 type of plane, so there are multiple planes like this. There's the first one, there's the second one, there's the third one, fourth, and so on. Okay, so there are similar planes arranged parallel to one another. So collectively we can identify these planes as family of planes. Okay, so these planes are used to find out or characterize the crystal lattices. Family of planes parallel passing through every lattice point. Convenient way to describe the orientation of any of these family of plane is within Miller indices, Miller index of the form HKL. So we'll have 3 in hexagon. In case of hexagon we have 4, but generally for all other lattices, crystal structures, we have HKL as the Miller indices of the plane. So we'll determine these 3 numbers corresponding to a plane, which will uniquely identify a plane and a family of planes. That means for all the parallel planes, whether it is number 1, 2, 3, 4 or 5, all the planes or all the planes in a family will have same Miller indices. So having Miller indices, that means we identify the planes collectively by using the Miller indices. So these are the planes which make basically the intercept on a unit cell. Okay, thus the Miller indices are reciprocal to intercept. We'll see how these are done. So that's the important note. If a plane does not intersect an axis, the intercept would be at infinity, and their reciprocal is 0. Uh, excuse me. Okay, so because there are planes which may not be intersecting any plane, so mathematically that plane will be meeting at infinity, and to accommodate this infinity into mathematical terms more precisely, more accurately, a reciprocal is done, which turns out to be 0. From here, this reciprocal word will be with you for quite some time in order to understand the properties of the solids. Okay, so reciprocal, why it is done? It is to make the mathematical explanation of the properties of a material more convenient. Okay, we want to make the theoretical concept as easy so that we can understand it better. So to do that, this infinity is converted into 0 by taking reciprocal, opposite. Okay, so this reciprocal, if the reciprocal of the intercept is a fraction, then each fraction can be multiplied each by each HKL values by the lowest common denominator. LCM and LCM we have already known. So now let us look at the these Miller indices for directions. So for example, we have a crystal structure. So we need to remember, if A is the so suppose this is the A, or this is the x-axis, this is the y-axis, so this is the y-axis, and this is the z-axis. Along the vertical is the z-axis. So A, B and C are the vectors along x, y and z, x, y and z, x, y and z. So alpha will be the angle so alpha will be the angle between B and C. That means not as A. So if it is alpha, so this will not be, I mean removing the axis other than corresponding to x will make angle alpha. So if this is x here, so this y and z will make the angle between y and z will be alpha. Similarly, if you are talking about beta, so beta along say y-axis, so the vectors other than the vector along y, that means A and C will make beta. So this is A, that means x-axis, and C along the z-axis, so that is the beta. And similarly for z, say gamma, so the vectors along x and y will make the angle between them as gamma. So this is the notation, and this is the lattice translation vector for any crystal structure, which R is equal to R1A, R2B and R3C. So this is the lattice translation vector, and A, B, C are the basis vectors. So we have known, we have studied this, and basis vectors are unit lattice translation vector. So when the position of the atom is switched by one atom at a time, so distance between two, the vector representing that direction, and the distance represents the lattice translation vector along all a x, y, and z directions. So now suppose note that their length are usually one lattice translation, not one length scale unit. Lattice translation, that means from one unit, one lattice point to the another lattice point. It's not one unit length, and so on. So how do we basically find out the lattice Miller indices? So to find out the Miller indices, we have various steps. So suppose we have this as the two-dimensional lattice. Fine. So I want to find out, suppose this is the Miller indices for a direction in 2 dimensions. I have from the origin O to this point. Uh, let us have the name A for this particular points. From O to A, there is a direction. Fine. So if we want to find out the Miller indices for the direction, so what we'll do, we'll drop a perpendicular. I mean, we'll simply find the components of this vector along x and y axis. This is for the 2 dimension, and similarly for the 3rd dimension or z in case of 3D, if we have the 3D. Okay. So then we will have the components of this vector along x, y, and z. So the intercept. So what we will find first? The intercept of the along the axis in terms of the lattice constants A, A1, A2, and A3. So from this, first is the intercept. Suppose along x-axis there is 1, 2, 3, 4, and 5. So there are 5 A units. Similarly, along y-axis there are 3 B. So intercept plane in terms of the lattice constant A1, A2, and A3, and the axes may be those of primitive or non-primitive unit cell. These axes may be, I mean, once you have selected a primitive or primitive unit cell, so in terms of that unit cell, these intercept can be, okay. The integral coefficient of each intercept, that means U, V, and W, are written in the braces. So we are talking about a direction, and these directions are say written in this kind of brackets. So these, for example, 5 and 3. So they indicate the lattice point plane intercept. So we have in the lattice translation vector, see R1A, R2B, R3C. The value of R1, R2, and R3 or UVW comes from the intercept the vector makes onto the x, y, or z axis. Okay. Now, because these intercepts, suppose there is a lattice. Suppose we are we want to find out the Miller indices for this direction. The direction is this one. Okay. So in 2 dimensions, along y-axis it has the intercept as b, that means 1 into b, so 1, and along x-axis it doesn't intersect, it is parallel to x-axis. So if you look at the intercepts, then basically these intercepts will be 1 and infinity. So dealing with the infinity is not recommended. So what is done is take the reciprocal of the intercept. So UVW, we need to take reciprocals. So for this the reciprocal is taken, so 1 by 1 and 1 by infinity. So this becomes and reduce them to 3 in case of 3 dimensions, 3 integers having same ratio. So we can reduce them, so this becomes 1 and 0. Okay, so 1 and 0 is basically then uh, the result expressed in the parenthesis HKL are crystallographic indices of the these planes. So if I now this becomes the, so because this is the plane, so the Miller indices of this plane is 1 and 0 for 2 dimensions. Fine. What are the steps? Steps is first find the intercept. First find the intercept and then take the reciprocal and then reduce. This is the third step. Reduce them to 3 integers having same ratio. Usually smallest 3 integers is taken. So there are 3 steps. One is take the intercept of the direction along the x axis, y axis and z axis. Take the reciprocal. Why we are taking reciprocal? To accommodate infinity, to accommodate the possibility of infinity. Infinity may not be in each and every plane. We'll see a few examples, but these steps should be applicable to all sorts of possible planes. So first intercepts, then the reciprocal, then reducing those reciprocal to smallest integers and whatever we have that cannot be a ratio, that should have that has to have a number in HKL. So the HKL in these brackets and these parentheses represent the crystallographic plane or the Miller indices of that plane. So HKL is the smallest number evenly divided by U, V and W. So if U, V and W are the intercept of a particular direction along x, y and z respectively, then the reciprocal reduced to smallest 3 integers is the Miller indices of that particular plane. So Miller indices are useful because parallel plane will have the same set of indices, and the set of planes so described is referred to as the crystallographic planes. Let us look at examples. So this is for 2 dimensions. Now suppose another 2D example if you look at. So suppose there is this particular point and the origin is somewhere above than this. So for when both the intercepts are in a positive direction, we have seen say 5 and 3 in this case, and if they are, one of the axis is along the negative axis, what happens? This intercept is -2 because the intercept is at the minus y direction. So -2 is represented for the direction as putting a small bar at the top of the number. So it becomes 2 bar. So bar represents that the intercept is along negative direction of that particular axis, and then suppose in this case there is a common factor. So common factor is generally taken out, and Miller indices is 2, 1 bar minus 1 bar. And this is, suppose now these points represent a 2-dimensional lattice. So there can be multiple planes that are equivalent. So all these planes represented by the dashed blue lines are same planes, set of directions represented by the Miller indices, this 2, 1 bar. So if this is the direction from the origin to 4 with a point 4 minus 2 as a coordinate, so all such planes which are parallel to this this one, this, and all of these planes are parallel. Okay, so all the parallel plane will have the same Miller indices. Fine. So in this case, this is for 2 bar, but because 2 is a common factor, that common factor is taken, and 2 1 bar is the Miller indices for this two-dimensional direction in two-dimensional lattice. This Miller indices represent a set of all such plane vectors which are, say, parallel to one another, originating at a lattice point, ending at the lattice point. Suppose, okay, so these are the three. If there is an arbitrary direction, what should we be doing? Suppose there is this direction from point 1 3 to say 5 minus 1. So what needs to be done is subtract the coordinate of end point from the starting point of the vector denoting the direction. For example, if the starting point is 1 3 and the end point is 5 minus 1, the difference, that means b minus a, would be, so this will be 5 minus 1 for x-axis, the point intercept along x-axis, 5 minus 1, and the other one will be minus 1 minus 3. So both the coordinates will be 4 minus 4. Okay, so this is what it is, and using these, now the intercept and finally the Miller indices can be calculated. So and if we are magnitude, we can write, the 4 can be taken out, and this is the Miller indices, and the magnitude. So the direction of the vector is 1 bar, and magnitude, we know what is the magnitude of the vector from a point, simply sum of the squares, square root of the sum of squares okay, of the multiples of coefficients of along each direction. So in this case, for example, 1 and 1 bar are the coefficients along x and y respectively. So square root of the sum of squares, that is the magnitude. So magnitude and direction we can find out. So this is the square root of the sum of squares. So this is the length of the vector is represented as square of the sum of squares, and these are directions or Miller indices of a direction. We need to remember there are certain notations. How do you write the square bracket? Then we have this common bracket. So for this, there is a naming convention. If there is a normal brackets, it represents the plane. Okay, so it represents the plane. Miller indices of a plane determined by all these steps. Find the intercepts, take this inverse or reciprocal of the squares, reciprocal of the intercepts, and then find out the lowest number to make all the values integer. All those are fractions to be reduced to a number. So once you're writing the Miller indices in the normal brackets, that will represent the plane. If you're using the square brackets, then the vector normal to the plane. So these square bracket will represent the direction, the vector which is normal to the plane. Okay, and if it's a curly brackets, then it is a set of all symmetrically equivalent HKL. That means we're talking about family planes. Okay, and if it is like this, so there is a family of directions. So H, E, L, there is a family of normal vectors. So if we look at suppose Miller indices of different planes, will this is just example. We will in the next few examples we'll see how basically these are calculated. So if we have discussed here for 2 dimensions, if you look at for 3 dimensions, so these greens are basically the phase diagonals, and this is a simple cubic. So if you look at suppose the Miller indices are, suppose this plane which is parallel to y as well as z, which is parallel to x and z. Sorry, here y is along this axis. So basically this plane is intersecting the y axis and it's parallel to x axis. So what is the first step? First step is look at the intercept. So along x axis the intercept is it intersects at infinity. Along y, suppose it intercepts at the unit edge length, and along again z intersect infinity. And the second point, the reciprocal of these, 1 by infinity, 1 by 1, 1 by infinity, and reducing these number to the integers. So 1 by infinity is 0, 1 by 1 is 1, and 1 by infinity is again 0. So what will have the Miller indices for the direction is in the square bracket 1 0 0, or for the plane that intersect at this particular point is the 0 1 0. Okay, similarly now if you look at, because there are 6 planes that constitute, that make a cube, so all these 6 planes are actually symmetrical, same, identical, constitute a family of planes. Okay, so what it means, what kind of Miller indices I can have. For example, if I take another, say, plane onto the other side, this one, plane parallel to the one we have just discussed. So now if you look at, because now this is origin, is this plane is passing through the origin, or if I look at the direction, then direction, for example, from origin to this plane, and this plane passing from origin. So in this case I need to shift the origin to a point which is at a point which is the intersection of that parallel plane with the same axis. So then the direction becomes from, say, this point at y to this, that becomes the direction. And now the intercepts can be taken similar to this, because this is y axis, so it will be, the intercept will be at infinity, -1, and then again infinity, and the reciprocal of these will be 1 by infinity, -1, sorry, 1 by -1, 1 by -1, and 1 by infinity, and therefore 0 1 bar 0 is the direction, Miller indices for the direction, and for the plane 0 1 bar 0. Similarly for all the planes forming, so top and bottom, side by side, and front and back, so 6 planes, the Miller indices will be now I can write this way. So 0 1 0 we have just seen, and corresponding to it there is 0 1 bar 0. इन दोनों को अभी हमने देखा. अब इनके इक्विवेलेंट क्या क्या होंगे, मैं फर्स्ट से लूँ. So this one can be at 3 different places, 1 0 0 and 0 0 1. Okay, and similarly the other one, uh, it could be 1 bar 0 0 and 0 0 1 bar. So this is the family of planes. So family of plane can be represented as curly brackets and then 1 0 0. That means uh, this plane is representing all the planes. So in a cubic, in a simple cubic, all the planes that are at the unit distance from the origin along x, y and z direction, all of them can be represented by this particular single Miller indices for the family of planes. Okay, so there are, for example, various planes in case of the crystal lattice. Suppose on to the left hand side, if we are talking about this this plane, so along say x-axis, this is 3. Along x-axis it is having the intercept at 3, and along y-axis it is intersecting at 2 times the lattice translation vector along x, y and z. Here it is along y, and in case of the z-axis, it is 2 intersecting at a point which is 2 times the lattice translation vector. So the intercepts become 3, 2 and 2. So if I take reciprocal, 1 by 3, 1 by 2, 1 by 2, and then reduce them to the number, so I can simply multiply by 6, and so it becomes 2 3 3. So 2 3 3 becomes the Miller indices of the plane. Or I mean, if you need to accommodate, अब देखिए इसमें अगर मुझे इंटीग्रल मल्टीपल लेना है दैट इज ट्रांसलेशन वेक्टर का, तो एक तरफ एक्स एक्सिस की तरफ 3 पे इंटरसेक्ट कर रहा है, y और z में 2 2 पे इंटरसेक्ट कर रहा है. Suppose I want to accommodate this, because there are family of planes that are parallel to one another, so I can accommodate this particular plane as well in the one unit. For example, अगर राइट हैंड साइड में मैं इसको देखूं, यहाँ पर मुझे सेम प्लेन लेना है. So with same plane with the Miller indices at 2 3 3, what it represents, the intercept, suppose ये x axis में 2 है, so intercept along x axis divides. तो suppose मैं यहाँ पर इसको ड्रॉ कर रहा हूँ, जैसे जैसे हम कह रहे हैं, दिस इज सपोज x एक्सिस, x एक्सिस यहाँ पर इधर है, तो दिस इज सपोज x एक्सिस, दिस इज y एक्सिस, एंड along the vertical this is z axis. So Miller indices 2 3 3, what it means, x axis को ये दो भाग में डिवाइड कर रहा है. इट इज डिवाइडिंग द यूनिट ट्रांसलेशनल वेक्टर इनटू 2 equal parts. Okay, so that where it will be, that point that will be somewhere in the middle. Along y 3 means it is dividing the unit translational vector in equal 3 parts, so I can write it something like this. So there will be 3 equal parts, and similarly for z axis also. Fine. So then I will join the points that points that identifies the plane. So this is the plane, because you know this plane onto the this side, as well as what we have drawn, they are parallel to one another, so they will have their, they are from the same family, they will have similar indices. So in order to draw the plane in the unit cell, what analogy I will draw? I'll draw that the first letter represents how many equal parts the intercept is dividing the lattice translation vector. x एक्सिस है अगर यूनिट लेंथ a है, तो a को वो a/2 पे इंटरसेक्ट कर रहा है और दो पार्ट्स में उसको बराबर डिवाइड कर रहा है. सिमिलरली यहाँ पर 3 है, दो सेकेंड लेटर इन दी मिलर इंडिसेस रिप्रेजेंट्स हाउ मेनी इक्वल पार्ट्स दी intersection divides the unit lattice translation vector into. Similarly on the z axis. Fine, hope this is clear. So suppose there is another plane, so Miller indices is say 1 2 2. So in normal terms, so along x axis it is intersecting at 1 times the lattice translation vector, 2 2 in the y axis and z axis at these particular points. So what it means, the x axis it is dividing in it is whole single unit, and y axis it is dividing the unit translation vector into two equal parts. Similarly on the z axis are the two equal parts. So that way you can draw the plane. So so this is the 1 to 2 plane. Some equivalent parallel plane is presented by the Miller indices. This, so if this is a 1 2 0, so 1 2 0 plane means it is intersecting at the x-axis and y-axis at 2. So suppose this plane, so along y-axis it is x-axis is 2 times than the y-axis. So x-axis if it is 1, y-axis is 1, x-axis is 2. So if I take the try to calculate the Miller indices of this plane, so the intercepts are 2 1, and suppose it is in parallel to the z-axis, so then reciprocal 1 by 2, 1 by 1, 1 by infinity, and then this becomes 1 2 0. So okay, so so this is how the planes, the Miller indices corresponding to the planes are.
Sir, class, sir,
okay.
second class start होने वाली है.
Okay. What's the time? I hope this is clear. If there is any doubt, we'll take up the doubts in the next class, because the time is for this class is as you have said, it is already over. So let me end this meeting and see you.